This is Jenny Sanders, and this is Lab 7. For this lab, I made a computational model that would analyze a star's motion to find the net force on the star. With this problem, this net force is due solely to the gravitational force of a black hole, and we were able to find that using the black hole's position. So, looking at my code, you can see that the mass of the star is given right here, which we will later use to find the force. The delta T is 1 day in seconds, right here. For each point in the data set, which we include the data set right here, a while loop, use right here, finds the delta X and delta Y, which are the changes in position. From these, I found the velocity in the X and Y direction by saying velocity equals the change in position over the change in time. So using the positions, using the change in position, we were able to find the X component and the Y component of velocity. Using those, we were able to then find the vector form of the velocity initially and finally by plugging in the X velocity, Y velocity for both parts. Because we know that momentum equals mass times velocity, we're then able to find the initial momentum and the final momentum vectors right here, just by multiplying the star's mass times each component of the velocity. Then we could easily find delta V, the change in velocity and the change in momentum, V final minus V initial, and P final minus P initial. Now we're going to get to the momentum principle, which says the change in momentum equals F net times the change in time. So we can also, using this problem, this is curving motion, so that means that dB dt, the change in momentum over change in time, is going to be set up in two components. It's going to be equal to dB dt parallel and dB dt perpendicular. Since we just said that the momentum principle sets F net equal to dB dt, we can also say that F net right here equals F net parallel plus F net perpendicular as well. So in my code, I said that dB dt equals the change in momentum over change in time, which we know, and that using momentum principle, we can say F net equals dB dt. The parallel component of F net and of dB dt is equal to the change in magnitude over the change in time times the unit vector. So we're going to find the unit vector, which is going to be the momentum divided by the magnitude. Then we are going to find that parallel component by saying multiplying the unit vector times the change in magnitude over the change in time. So we got that right here. Knowing that that parallel component equals that, we can say the same thing for F net, and then we can subtract the parallel component from dB dt and set that equal to the perpendicular component and say the same thing for F net. So now that we know the components, we can examine how these affect the star using the arrows. So right here we got the arrow set up. Hold on. Right here. So I'm going to run this code. So you can see the blue arrow is the arrow that shows the parallel component of the force. The red one is the F net, and the black one is the perpendicular to the motion. For my what does it mean question, it says what are the similarities and differences between F net and dB dt demonstrated by the arrows. So in our arrows, we set the arrows equal to F net, parallel, perpendicular, and F net. And the net force is the total sum of all of the forces, so we know that. And then dB dt is found by observing an object's motion. And because of the momentum principle, we can see that dB dt is equal to the net force. So if we were to replace these with dB dt, perpendicular, parallel, and then dB dt net, we could say the same thing. The arrows would show the same thing. At the end of my code, we were trying to find the mass of the black hole. We knew the position of the star, the position of the black hole, the magnitude of the force, and the gravitational constant. Oh, and also the mass of the star. So we're going to use this equation right here, the gravitational force equation. So we know those things, and we're trying to find the mass of the black hole. So I rearrange the equation right here, and I am going, after it's run, I can set it to print the mass of the black hole. So right here, it says the mass of the black hole is 3.566 e to the 31st kilograms. And I checked that into my WebAssign, and it said that it was correct. So that is the mass of the black hole. For my what if question, if the black hole was replaced by a different black hole but at the same location, and the motion remains unchanged, only affected by the gravitational force, then the mass wouldn't make a difference. The same position would be put into the equation, so the same mass would come out. So if we put in the same position in the equation that got the mass of the black hole, the only thing affecting it is the position. So the mass wouldn't change, since the gravitational force is the only thing affecting it. Otherwise, we would not be able to tell. So, for my conclusion, the lab showed how using basic ideas such as the momentum principle, the curving motion ideas, and the gravitational force equation can help you analyze an object's motion and find any unknowns that you want to know.